The goal of this project was to evolve a robot to visualize the closest object to its body and move towards that object. Some of the milestones implemented in this project include adding blind runs in sexual reproduction, creating randomly varying objects in the environment, using proximity sensors to determine the location of an object and update the fitness function in neural networks to cause the robot to navigate a course. I was able to develop a neural network that allowed for the evolution of a robot that navigated a course randomly, finding an object at any given time, but found it very hard to satisfy the requirement of finding the closest object without strictly forcing the robot to find that object. The neural network utilizes a binary representation of the collisions of the raycast at any given time and uses the detected collision from a ray to find the relative coordinate location and Euclidean distance from the object. These values are added together and then multiplied by the 32 synapses that are the weights for the joints and sensors of the robot initially. The video that is currently playing is a sped-up version of a simulation that shows one of the best evolved robots that is randomly navigating a course of objects during a given time frame. The fitness function shown here is merely represented by the number of collisions detected during the simulation. I decided that I wanted to take it a step further and chose to attempt to minimize the time between any given collisions as well as maximize the number of collisions of the robot within any object. The next video shows an evolved robot that has minimized the time it takes to collide with an object. You will notice that the robot only regards the time and does not attempt to find another object after its collision. In order to fix this, I attempted to evolve them both together and found that the unevolved simulation is with no immediate intent or direction. Given enough time in this next simulation, the robot will eventually contact an object, but takes a very long time to do so and is not very efficient. We can compare this unevolved robot with an evolved one that attempts to minimize the time to collide and is significantly faster. We can hope to assume that given more time, this robot would have changed its momentum and found a new object. It was extremely difficult to evolve a robot that attempted to maximize both fitness functions and seemed to take advantage of the efficiency of minimizing its time. The algorithm found this as a loophole and took this as the easy way out whenever possible. I attempted to combat this with a few constraints but was unsuccessful. The algorithm was still able to show that evolution occurred, and we can visualize this with the fitness curve that is shown. I found that it could not be easily proven that sexual reproduction was beneficial, and having objects that randomly change their positions were very difficult to overcome. If I had more time, I would investigate more constraints to hold both fitness functions to. I believe that if I were able to both maximize the number of collisions and minimize the length of the time between any two collisions, then the robot will eventually try to find the quickest timed path to any given object, hence finding the closest object.